What is organic chemistry? It's all about carbon. And we haven't really talked about carbon. We've been dealing with, inorganic salts, all these kinds of things. You got the metals on the left and you got the non-metals on the right. But carbon is its own beast. And that's why we kind of give it its own aspect of chemistry. Organic chemistry isn't overly an old thing. It's kind of a newer thing than, it deals there with the chemistry of carbon. And I'm going to tell you guys there later that, your phone, everyone's got to have the new iPhone, the new phone. This has got a better camera. This and that. Don't buy any more phones. The whole world is going to change. And I mean in the next year or two. That's what at maximum 5 years. So maybe you will need a new phone. Because I bought this thing there 2 years ago and it's already on the fritz. Makes me mad. You buy things there these days and they're only designed to last for a year or two. But let's get into it, shall we? History of organic chemistry. Basically, chemistry started there with alchemy back in the Dark Ages there to change wood into gold. Which we can actually do now, but not with normal chemistry. We use, see what I mean? My brain isn't working there today. It's really not. Nuclear chemistry. But it all started there. I actually went to this school in Prague, Czech Republic, Charles University. I was there for a semester. Prague, really fun. Really fun if you ever get a chance, go. For some reason, I think it has the highest, the greatest amount of torture museums per square kilometer than anywhere else in the world. Yeah, they did some weird things there in Europe. But it all started there with this guy, Wohler. And see, before organic chemistry, any fluids, anything, from a grasshopper or a squirrel or us or anything, that was living, we couldn't reproduce or synthesize any type of compounds from, a living organism because it had some higher being quality to it. And us being just lowly beings, we couldn't possibly produce anything that, is living, came from a living organism. Well, as it turns out, that was a bunch of malarkey, okay? Because this guy synthesized urea, P, all right? And it changed the entire way we think. Because in the lab we could create an organic compound, a living compound, and it changed everything. Okay? And it's all, carbon is a very, very, very strange beast. It has a unique ability it can bond in large chains, it can go into rings, and there basically is no limit to carbon chemistry. And we'll show you this there. It's kind of interesting. Before I begin, you see carbon, and if you have a periodic table, or my periodic table that I gave you, the oxidation number there for carbon, if you'll see it, it's on mine there, that cheap one I gave you guys there. I hope it helped anyway. Carbon has an oxidation number of plus or minus 4, right? Because the magic number in chemistry is 8, and carbon is right in the middle. It has 4 electrons on the outside. So, have a look at carbon, this carbon right here. How many bonds does it have? Well, the carbon is bonded there to the nitrogen. The carbon is double bonded there to an oxygen. And carbon is bonded there to this nitrogen. Carbon has 4 bonds. Write that down somewhere. Know that, because that will influence the next 6 weeks. Carbon will have always 4 bonds. Okay? Organic chemistry, history and scope. The list goes on, and we're getting more and more and more and more. Nutrients, fuel, fabric, fuel, gasoline. Like you even look at a nut, like an almond. Don't try this, but I've tried it. And, you put an almond on the end of a pin or something, or a fork or something, right? Stick it in there somehow. And then you can actually, you light with a lighter there one side of the almond. And this thing will burn like a candle. And it'll keep burning. And, until... And and candle, there's an organic chemistry. Wax. We'll get into all that kind of stuff. Makeups, paint and varnishes, plastic, dyes, soap and detergents, cosmetics, medicine, all these kinds of things. Like the list is just keeps growing every day. I've got these multiple choice questions here made throughout, and I changed this PowerPoint. I apologize for the lateness. It went out there yesterday. Just teaching styles. All my PowerPoints were made for in class, and now you kind of change them there to VR. And I had normally I would ask you guys this question without the answer, and then I would click, and then the answer would show up. But I'm not doing that because it's just not the nature of the beast. But which chemical formula represents an organic compound? Now, good question. You'll see it again. Promise, promise, promise. So when you see organic, okay, first thing you think of is carbon. Okay, and so here I've got silicon dioxide. No carbon. Sodium hydroxide. No carbon. Here I got 3 carbons and 8 hydrogen. Well, there's carbon, so there's a possibility. This is actually propane, which you will know. And here I got agua. All right. Another example that I could throw at you is CO2. And that's a small 2. I'm just too lazy to... actually, no, I'm not too lazy. There we go. Now you're looking at this one here. Well, hey, wait a second. Carbon dioxide has got a carbon in it. But this is not an organic compound. Okay? It's an organic compound. You'll start to see what we're dealing with there as we go on. But there's carbon and hydrogen, nitrogen, oxygen, these kinds of things. You'll start to be able to differentiate between an organic compound and not. So just be careful. CO2 is not an organic compound. Even though it has a carbon in it, which I'm completely contradicting myself and probably confusing you more than ever, but we'll all get there. Carbon, Lewis structure. Okay, it's got these 4 valence electrons, and they all hang out in these areas. Kind of opposite, right? And it's this structure that allows carbon its versatility in making organic compounds. The list is endless. Okay, atomic number 6. Here's your electron structure, 1s, 2s, 2s2, and 2p2. Valence electrons 4. Carbon will always have 4 bonds. I'm going to open this up a little bit so I can see what's on the horizon. There we go. Okay. So, classification of organic compounds. Organic compounds can be saturated, or they can be unsaturated. Now, if we go back to what we learned there in solutions there, I think it was week 2, we were talking about salt going into water or sugar going into water, right? And then the solution can't handle any more salt, solute in it, so it's now full, it's saturated. But if I can add more than the solution, we call it unsaturated. We're still going to use the same principle. Saturated means full. Unsaturated means not full. But here we're talking about hydrogens. Saturated organic compound means 2 things. Number 1, the carbon-carbon bonds are 1. So if you look at this carbon here, it's singly bonded to this carbon. How many bonds does carbon have to have? 4. So that means that here I have hydrogen, hydrogen, hydrogen. I have the maximum amount of hydrogens that I can have. I can't get any more hydrogen on there because carbon will only have 4 bonds. So saturated organic compound means carbon-carbon single bond, and all the spaces there are filled there with hydrogen. So what would be my chemical formula for this? C2H6. Okay? Unsaturated organic compounds, not full of hydrogen. See, I have the same number of carbons, C2, C2. But because now carbon can have a double bond and it can have a triple bond. Can't have 4. Okay, so the max carbon can have carbon-carbon single bond, which means it's saturated. Carbon can have a double bond, and look what it does to the number of hydrogens. They're decreased because carbon can only have 4. So see this carbon here? It's got 1 bond, 2 bond, 3, and 4. This one here is the same. Okay, so this is unsaturated. And carbon can have triple bond. That's the maximum it could ever have. It'll be single, double, or trip. Okay, so a double and a triple bonded carbon, these are what we call unsaturated. All right, and if this was carbon triple bonded to another carbon, I would have to whack one of these hydrogens on this side and whack one of the hydrogens on this side. So it means that there'd only be 1 hydrogen here, 1 hydrogen here, carbon-carbon trip. That would also be unsaturated. So to recap, saturated, carbon-carbon single bond, maximum hydrogens. Unsaturated can be double or triple bonded carb, but then we got to whack some of the hydrogens off because carbon can only have 4. Saturated, unsaturated. Today we're going to kind of deal with mostly saturated. Next week there we'll deal with unsaturated, but this is how we do it right here. The carbon atom bonding and shape. When you have a look here, all right, carbon can form these chains. And this is the versatility here with organic chemistry. Like we've got 1, 2, here, I'll blow this up a bit here so you guys can see. I got 1, 2, 3, 4, 5, 6, 7. 7 carbons. And they're all in a chain. And you look at this here, is it saturated or unsaturated? Well, unsaturated means that there has to be a double or a triple in there somewhere, and there isn't. Here all the carbons are single. I got maximum hydrogen here, so this is a saturated hydrocarbon. Hydrocarbon. Okay. You look at this one down here. Don't worry about the name. I'll teach you guys a different naming, the naming system. But you see here now, I do have doubles in here, and I can have, this is how there is no end to organic chemistry. Because, look here, I have heptane. I have 7 carbons on here. Well, what if I just whack this hydrogen and put another carbon on? And then maybe put another carbon on. Maybe I whacked this hydrogen and put a carbon on here. And I have another chain coming all the way up here. There's no limit to the amount of organic molecules that we can make. And it's proving very profitable in the business world as well. Okay, so but another reason carbon can form so many compounds is the carbon can link together. Okay, all we need to do is add another carbon to this molecule, and now we've completely changed it. Like, look, this is heptane, straight chain. Okay, and it's got 7 carbons. Well, if I whack this hydrogen, put another carbon on here. Now it would be octane. Completely different banana. Different physical properties, different chemical properties, different. It's completely different. Look at this one, vanilla. That's the chemical structure there for vanilla. And you see carbon can be in rings, but you will notice, doesn't matter. Look at these carbons. They all have 4 bonds. Here, we'll look right here. This carbon, 1, 2, 3, 4. This carbon here, this is benzene. This is a little different. We'll get into benzene there next week. Okay? There are things going on in benzene that this diagram really doesn't show. But we'll get there. We'll get there. This carbon here, 1, 2, 3, 4. Everything else is following suit. So, now, you guys will remember this there from 1008. Now, how much am I going to test you on? There might be a question or two here or there about bond angles. You'll remember there, Vesper states that electrons repel each other, which is the reason why water is bent. Because here's your oxygen. These are your hydrogens out here, right? But oxygen has these pair of electrons on the top of it, which then push those hydrogens down, which is why water looks bent and gives it its unique chemical properties. But you'll see here in this tetrahedral shape there, carbon-to-carbon bond is 109.5. Sorry if you can't see that, but it's in there, okay? Here we've got this one here, which we'll get into there when we get into double bonds. One of the things I want you guys to work on is your ability to see these flat molecules on my slide piece of paper. I want you to start envisioning them in a three-dimensional manner. Okay? You look at these ones right here. No, I'm not going to get into that right now. But start thinking 3D. Can you picture yourself on the backside of this molecule looking towards yourself? I have no idea if that made any sense. Let's try that again. Like we're looking at it from this, I'm looking at it. But picture yourself being on the backside of the PowerPoint. Can you envision seeing this molecule from different angles? Because molecules are not flat. They're not two-dimensional, they're three-dimensional. And if you can expand that kind of vision to start seeing things three-dimensionally in space, even though the only mode I can give it to you is in 2 dimensions, that will help you a lot. Okay? So you got 109.5, 120, and then here we have a linear, okay? Linear shape, which is 180 degrees. It'll all come forward in a little bit. I'm going to blow in on these ones as well. Be prepared to see, and you'll see here, this is propane. 3 carbons, 8 hydrogens. This is also propane, written in stick form. Here we've got what we call the condensed structural formula. And you have a look here. Carbons on the end. You see this carbon here, carbon, carbon, carbon. This carbon here, 3 hydrogens on the end that are bonded to this carbon. CH3. Whenever you see a CH3, that'll be an end carbon, or what we call a terminal carbon. This carbon here on this side, it will be CH3, because carbon has 4 bonds. There's 3 hydrogens here. The 4th bond is attached to the carbon. So there's your CH3. If you see a CH2, okay, then that means that generally this is going to be an inside carbon. But not necessarily true, but I'll show you different ones, okay? So CH3, CH2, CH3. These are all the same, and be prepared to tackle them at any given point in time. The line structure. This is how biologists, we just write things out very quickly. Bang, bang. When we're dealing with a hydrocarbon, hydrocarbon is just hydrogen and just carbon. Okay? Methane, ethane, propane, butane, pentane, hexane. Those are hydrocarbons. These are all mean the same thing. Even though this one here looks kind of ridiculous, be prepared. If you see something like that, that means that, oh, there's a carbon, there's a carbon, and there's a carbon. That means there's 3 carbons in here. And because there's nothing else, this is all hydrogens. We'll get it. I'm just introducing stuff. Here's a little bit of a three-dimensional model. Okay, same thing. Okay, CH3, CH2, CH3. And what we call the space filling model. Same thing. Okay, so just different things that you will be able to, you'll see them. You'll see them on the assignment. Okay, and you'll have to handle them all the same way. All right, you have a look here. Here we have the condensed structural formula. So CH3, CH2, 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 CH2. See, all those are interior carbons. And then here I have a terminal, CH3. So I go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Same banana. Okay, so there's a condensed structural and a line structure. Oh, while I have it in my brain, the questions that I have, please let me, I hope you guys have the textbook or an e-textbook or something, okay, that you guys have, because the questions are posted in the syllabus. Week by week, it's all the questions there. And here in each week, I will give you the answers, all right? But if it doesn't really help if you don't have the questions. Let me know if there's a whack load of you that don't have the book. Oof, man, that'll be tough. But you can kind of get the gist of the answers here. If you don't want to buy the textbook, you see basically what we're talking about here, like for this one, CH4, okay, I just wanted you to write the Lewis structure. You know, all the electrons, this and that. Being able to name a compound if I give you a structure, or if I give you the structure, you give me the name. So even if you don't have the textbook, by the end of today's class here, I'll show you how all these work. I know it looks pretty crazy, 1-chloropropane and all this kind of stuff, but honestly, there's two slides in this that if you can nail those 2 slides, the rest of the semester will work out well. Okay, so let me know if there's any issues, but the answers are posted in there, and we'll get there. This is what we're going to be covering for the remainder of the 6 weeks. This week and next week there, we're going to be dealing with hydrocarbons. Okay, hydrocarbons, they, oil, gasoline, petroleum, propane, these kinds of things. There's a lot of energy in the what we're going to be talking about there today and next week. They're hydrocarbons. That's why we use them as a fuel source. Okay, and even breads, rice, lots of carbon and hydrogen in those. Huge amounts of energy. Okay, but when we get into, I think we'll start a little bit there next week. We get into these functional groups, and there are alcohols. They are OH. And you can see what an alcohol looks like. Okay. An aldehyde functional group, we write it CHO, but this is how it looks like. Okay. C double bonded to an O with an OH, or with an H there. Ketone. Here we have a carbon group on this side of however many carbons. And here we have a carbon group on this side with however many carbons. Okay? And in the middle of it, we have a carbon double bonded to an O. Carboxylic acid. You guys have seen these there before. Okay, it's C double bond. There's a C in here, double bonded to an O, double bonded to an OH. An ester. All right, which is a C double bonded to an O, also bonded to another O, and that O is attached to another carbon group. We'll get there. I'm just introducing these, and you don't have to memorize these by any means. But all these different functional groups, they affect the chemistry. Amines and carboxylic acids, This is the chemistry of amino acids. An amino acid is a very, very small molecule with a carboxylic group on one end. Carboxylic group is right here. And then on the other end is an amine group. And one acts like an acid, one acts like a base, these kinds of things. And there's also an amide when we're dealing with proteins. So it's a good thing. Is it necessary right now? No. But by the end, you better know these like the back of your hand. Okay, so that's something there to work on. All right. Right now, no. Let's just work on there today's, let's get the intro to organic chemistry, because if you can bang out there today, the rest of the semester will be nice. Okay? Hydrocarbons are organic compounds that only contain carbon and hydrogen. And yeah, man, they can get massive. Massive. And the more carbons you add to a chain, the more solid this thing becomes. It's the difference between propane, which has 3 carbons, and then you have beeswax, which I think has 16 carbons. Don't quote me on that. All right, but we'll get into all that. Hydrocarbons can be broken into aliphatic chains, which are just chains, all right, of carbons. They could be in kind of a ring structure, but they're just normal carbons bonded to another carbon. There's nothing special. We can have double bonded carbons in here. We could even have triple bonded. But think chains, all right? Then we get into benzene. That's a whole nother ball game. And we'll deal with aromaticity there later, if not next week, okay? But aliphatic just means normal carbons acting normally, 4 bonds, either in a chain or a simple ring structure. I'll show you those. Aromatic, benzene ring, different ball game. We'll just put those into their own category and we'll deal with them there next week, okay? Hydrocarbons, fuels, lots of energy in them, okay? And when you burn these hydrocarbons there, you make CO2 and water and a massive amount of energy, okay? The world oil production, which I think is going to be going down. I think Ford just put an announcement out. They said by 2035, Ford is going completely electric, which I think is awesome. Okay. This slide here, you will see again right here. This is the most important slide of the entire semester. Okay, this one right here. We'll get there. Okay, I've broken it kind of in half just to show you that the number of carbons within an aliphatic chain has a name. 1 carbon, if there's only 1 carbon, it's meth. If there's 2 carbons, it's an F. 3, prop. 4, bute. 5, pent. 6, hex. 7, like the one there we just saw, hep. 8, oc. 9 is non, and 10 is dec. All right? And how this works is, and let's just go back here. I'll show you. Is this it? Yeah. Let's go to this one right here. Now, how would I name this? Welcome to the whole thing. Welcome to the next 5 weeks. I'm going to give you a structure. You tell me the name. I'm going to give you the name. You tell me the structure. That's it. So it is kind of a puzzle. And there is a systematic way of doing it. And once you get that system down pat, man, it just becomes more fun than anything. At least for me. Nerd fun. I like it. I like it. So you look at this right here. There's 2 aspects you have to do in order to name these things. Number 1, you must count the carbon. So I got 1, 2, 3, 4, 5, 6, 7. So there's 7 carbons. So this has to be a hept. something. Now, because all of the carbons are single bonded, it is now an ane. If all the carbons are single bonded, it's an ane. So that means that this is a heptane. So we can get methane, ethane, propane, butane, pentane, hexane, heptane, octane. Octane means there's 8 carbon atoms and they're all singly bonded. It is a saturate. All anes are saturated. Okay? And I'm just jumping back to where I was. Apologies here. So this is what we're dealing with here. In methane, it's just one carbon with one hydrogen, one hydrogen, one hydrogen, and another hydrogen. CH4. Okay? And ethane is 2 carbons, like this, 2 carbons with hydrogens, hydrogens all around. It is C2. What do you think? H6. And there's a formula for alkanes. Alkanes. CnH2n plus 2. Okay? So you can calculate the chemical formula of any alkane. That's what these chains are. Single bonded carbons are alkanes. And it has a chemical formula of CnH2n plus 2. I'll show you guys all these there when we move on down. And again, this is just kind of the same slide. And I want you guys to look at, here's methane. 1 carbon, okay? And it has a boiling point of negative 161, melting point of this. Ethane, C2H6. There's your condensed structural formula. Have a look. Completely different physical properties. Completely different banana from methane. When you look at propane, we keep adding carbon, which means we have to keep adding hydrogen. And you'll see how these things can get massive very quickly. And look at their boiling points, look at their melting points. Here, methane is a gas. And propane, you buy it at the gas station there. It's a gas at room temperature. Okay? It boils at minus 42 degrees. All right? But then you look at octane, nonane, and decane, and all these ones here. Okay? They are not gases at room temperature. We'll get into all these kinds of things here, but that's a really good slide there. 1 carbon meth, 2 carbon eth, 3 carbon prop. You have to memorize that. That is insanely important. So if I give you a carbon compound with 6 carbons, bang, it's a hex. Now, we'll get into more of that in a second here. Alkanes. They are carbon-carbon single bond. That's it. All right? And alkanes, you can figure out their chemical formula by using this little formula right here. So if you have 3 carbons, so that would be C3, H2 times 3, so that would be 6 plus 2, so C3H8. Okay? Look at this one right here. Any idea what that would be? Well, how do we do this? First thing you do, count the carbons. 2 carbons is an eth. The carbons are single bonded, so it is ethane. This one here, I think we did this already. And I put this on an angle just to show you that this is 3-dimensional. 1, 2, 3, 4, 5, 6, 7. And C3, C2, 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 C3. These are all single bonded. This is heptane. Look at this one. C3, C2, C2, C2. I got 5 carbons. Any idea what that would be? Single bonded, 5 carbons. Shout it out. Pentane. All right. And I want you guys to I put this on an angle here to remind myself that you look at all the bonds in an alkane. They're single bonded. Everything is single bonded in an alkane. There's no double bonds or trips. And we write this three-dimensional structure as a two-dimensional structure on a piece of paper, but I want you guys to realize this. In single bonded, when an atom is single bonded to another in organic chemistry, these guys are all rotating around each other. So you see this hydrogen, it's written here, but it's actually rotating. They're all rotating around this carbon atom. So this hydrogen atom could be down here. It could be. This hydrogen atom could be over here. These three hydrogen atoms are rotating on this carbon. This carbon is it has a bit of movement there against the other carbon. And these hydrogens here, they are rotating about that carbon. So this hydrogen here, you might as well say that it's here. You might as well say that it's here. All three of these guys here are interchangeable. Okay? Why am I saying this to you now? Because I'm going to come back to it later. Okay? So alkanes, single bonded carbons, they are saturated. They're full of hydrogens. Okay? And their bonds rotate about each other. Okay? And their formula is this one here. Which is the molecular formula for an alkane with 16 carbons? Beautiful question. You'll see it again. Okay? So here, I didn't even tell you, I didn't give you a name of it. All I said was that it's an alkane. Okay, what's an alkane? Alkane is carbon-carbon single bond. Okay, so there's no doubles, no triple bonds. So, okay. And it has 16 carbons. So, how do I answer this question? Well, you use this formula here that I've given you. CnH2n plus 2. This is the chemical. This is the general formula for aliphatic alkanes. So C16 H2 times 16, which is 32, plus 2 is 34. H16 34. Okay. Isomers. And I was going to talk about it there earlier, but I thought I'd just wait here. Have a look here. C4H10. So, 4 carbons, which we have right here. 1, 2, 3, 4. And I fill all the hydrogens up. So it would be C4H10. That is an alkane. And in fact, this alkane is called butane. It's the fluid there in a lighter. I know when you look at the lighter there, it's all liquid because the gas has been compressed. But when you take you hit the little plunger, the gas is allowed to release, or the liquid turns into a gas, and with a bit of a spark, boom, boom. Okay? But have a look at this one. Here I have 1, 2, 3, 4. Okay, that's C4. And let's count the hydrogens here. Well, this carbon needs 3 hydrogens. There's 1, 2, 3. And there's 1, 2, 3, 4. Oh my God, there's 10 hydrogens here as well. And this is called methylpropane. And these two are isomers of each other. Okay, I'll put that somewhere else. These two are isomers of each other. Now, what does an isomer mean? It means it has the same chemical formula, C4H10, but it has a different structural formula. And you'll see here that this carbon and its 3 hydrogens have been taken off of here and put onto here. And you will see there that they have the same chemical formula, C4H10, but completely different physical and chemical properties. So an isomer, the same molecular formula, different structural formula. Okay? Why not? Let's try it out. How do I name these? First thing, count your carbons. Find your longest chain of carbons. So 1, 2, 3, 4. So that's got to be a bute, according to my chart. All the carbons are single bonded, so it has to be an alkane, which means it's butane. Have a look at this one. Find your longest chain of carbons. Well, I got 1, 2, 3. 1, 2, 3. Hey, wait a second. What happened? Things have changed here. So you find your longest chain, 3 carbons. They're all single bonded. So this has to be a propane. And you'll see here that you have a side group off of here. And we'll get there. I'm probably confusing you more than anything, but it'll work out in the end. Hold on. Look at this one. Great question. There are 3 isomers of pentane, C5H12. Draw the structural formula for all 3 isomers. Now, on a testing situation, maybe on an assignment or a lab or something like this, I would ask you to draw it and I could see it. But generally, how you would do it is you would just choose A, B, C, or D. And that would be your, that's what we would be looking for there. But here's there are 3 isomers of pentane. Well, here, pentane, we draw it. There's your pentane. 1, 2, 3, 4, 5. And because it's an ane, all the carbons are single bonded. But then now we can start to play with these things now. And what happens if I take this carbon and put it over here? Now I have this carbon up here now, which is what we have here. You have something different. Okay? And we find our longest chain, which is 1, 2, 3, 4. So this is a butane. And then we have this group on here, 1 carbon, methyl butane. Now, before I move on, this may do more damage than not, but I gotta do it. All right? We just took this carbon off of here and put it onto here. And we got methyl butane. What happens if I take this carbon and put it onto here? So in essence, this carbon is not here, it's on here. All right? I don't want you. This is where
Ian,
Yeah,
can I
yeah.
ask a question?
Yeah.
So, because did it become methyl when it branched off like that?
We'll get there. I'm kind of jumping ahead to confuse you so that by the time we get to the slide that will, I hope, magically clear everything up. This is where you kind of miss a whiteboard and all this kind of stuff and having you guys there. But yeah, that's how many carbons is this one? 1. So it will be a meth. But we'll get there. That's a great question. Great question.
Thank you.
No, it's all good. I wanted to show you guys there that if I take this carbon and I put it over here, I get methyl butane. But if I take this carbon and put it over here, so this carbon is not here, it's actually here. Would you believe me that we get the same compound? Look at this right here. And now I want you to, with your head, with your brain, I want you to change it around 360 degrees. So I'd have carbon, 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 carbon. If I flip those around, they're going to look exactly the same. But where is this carbon going to be if I flip it around? This carbon will be actually on this carbon. Now, I probably confused you. You're probably throwing a book against the wall. It's all right. It'll come. All right? And you've got to start thinking 3-dimensional. Hopefully there you guys can see that. And if you don't, we'll work on it. Okay? And if this carbon is here I have methyl butane. If I turn it around, this guy here will be on, it'll be on the same carbon, but this carbon is now moved here. Hopefully there you guys can see it. All right? If you can't, we'll work on it. And pentane has another isomer. So what I did was I took this carbon, put it on here. And now I'm going to take this carbon and put it underneath. Welcome to organic chemistry. All you need to do is add an extra carbon, and you've now completely changed the ballgame. It's a different beast, different banana. Physical, chemical properties are the different. And what we have here is called dimethyl propane. Now, it's all right. I've got slides here that'll walk you through the naming system, but I want you guys to see the first thing you do in naming, find your longest carbon chain. So you see in this case here, it was 1, 2, 3, 4, 5. Okay, that's a pent, single bonded pentane. Here, 1, 2, 3, 4, longest chain. This is a butane with a methyl hanging off of it. Look at this one. What's my longest chain? 1, 2, 3, 1, 2, 3, 1, 2. Hey, my longest chain is only 3, so this must be a propane. So there's your chain. Can I do this right here? I'm going to insert a shape. So you have a look here. You find your longest chain. If I can do that. So there's your longest chain. So there's your propane. And I got a methyl and a methyl off here. Dimethyl. We'll get there. There's lots to, I'm just throwing stuff at you here and seeing what sticks. All right. So where did I go? Right here. Alkyl groups. These are the groups there that I kind of just talked about right here. They are the groups that are kind of hanging off the main chain. All right. And remember that all these guys are rotating. Single bonds are rotating, right? So your molecule could look like this. You got to find your longest chain, whatever it is. If it goes up like this or around like this, you find your longest chain, count your carbons. That's what it's going to be. And naming these guys, you kind of work from the back end forward. So here is my propane. Now, or here is my butane. What is hanging off the chain? Oh, there's a meth. There's a 1 carbon. So this is a methyl. That ol sound means that it's not part of the main chain. It's an alkyl group. It's a side group. It still follows the same method. 1 carbon is meth, eth, prop, but there's the ol, which indicates to me that it's now a side chain. It's not part of the main chain. So that's what these alkyl groups are. Okay? And they are groups that hang off. That's that. So here we have, this is methane. This is this is the molecule methane. Methyl is now a side group. So you have here, you look at this one right here. Here, if you wanted to name this, okay, you got to find your longest chain. Well, I could start here, 1, 2, 3, okay. 1, 2, 3, 4. Oh, I could even start here. 1, 2, 3, 4. Okay. So I could start from here, or I could start from here, but my longest chain is 4. So this is a butane. And I'm going to steal this. And bring it along with me. So, whoa. Stop doing that, man. There we go. So there's my longest chain. So that's a butane. And then I see here that there is a methyl group hanging off of it. So we would call this methyl butane. We'll get there. We're just throwing things at you. These are the names of they follow exactly the same as the other slide there. But you notice there, these all have these ol sounds. Okay? So methyl group, ethyl group, it's all based on the number of carbons. Nothing's different there. Okay? What do we got here? You will get into, you might see, I try and stay away from, there are old, I'm going to teach you guys the new way. Okay, it's called the IUPAC. IUPAC. IUPAC way of naming. Out in the field, there you will, like isopropyl alcohol. The rubbing alcohol, what you buy at Walmart there for, 50 cents for a bottle, and, good for cleaning cuts, hurts like a bugger. And that's how we know it. You go anywhere in the world, anyone knows isopropyl alcohol. It's a 1930s term. Okay? Really, we would call it 2-propanol. But we'll get there, all right? I'm not really too interested in the old school names. Like Jesus Murphy, if you guys can get the IUPAC names, man, I have done my job. Okay? So, but you'll see there that isopropyl alcohol, what happens, iso just means middle. That's about as far as I'll take it. You might see one question here or there, but iso means middle. Just where it's attaching. Let's have a look here. Now we're really getting into naming. Okay, the IUPAC naming was developed in an international science meeting in Geneva, 1892. The IUPAC name it's basically just a standardization. So people of different languages and wherever, there is some type of commonality. Because science shouldn't be based on language or where you came from. Science is applied natural law. So everyone can get involved in this, okay? Okay, now, welcome to the most important slide of the semester. You will know this by the back of your hand, and I cannot stress that enough, okay? What we've got here, I don't know why that's there, but I'm going to cut that out. The number of carbons. Okay, the prefix that attaches, right? If there's 6 carbons, it's got to be a hex. And if all the bonds are single bonds, it'll be a hexane. But since carbon is very versatile, if one of the bonds has a double bond, we call this an ene. So it will be a hexene. And carbon can have trips. That's the max. All right. And if there's a triple bond within this 6-carbon banana, it will be hexyne. Okay. We'll apply this. Once you get this, everything else will fall in place. Okay. And I'll show you guys some examples. Like, is there any on here that I can show you? No, I think we deal with dubs and triples there next week. Yeah, we'll just leave that there till next week. Okay. Next week we'll cover double bonds and triple bonds. But be aware. Hexane, hexene, or hexyne. And you'll notice there the formulas. This is how you calculate the chemical formula there for a hexane. CnH2n plus 2. If there's a dub in there somewhere, that means it's an ene. And that means that the formula there to find the chemical formula is CnH2n. Because what you've done is you're taking 2 hydrogens away and you're making a double bond. So that's why you don't have this plus 2 anymore. And when you go over to a triple bond, you're actually taking another 2 hydrogens away, unsaturated, and to make a double bond, which is why you have CnH2n minus 2. I will ask you in a testing situation to utilize these, so just have them ready to go. It's not mad. What is the chemical formula for a hexene with 5 carbons? You plug and play. That's how she goes. Practice problem. Give the IUPAC name for this alkane. Okay, great question. These are all good. So you look here and you're just going, what is going on here? So what's the rule? Find your longest carbon chain. So I got 1 carbon, 2, 3. No. 1, 2, 3, 4, 5, 6. Okay, so that's a hex. And I'm going to show you guys how to do this. And you notice that I'm starting from the back side working forward. You will have to as well. So that's a hex. This is an alkane, so it's all carbon-carbon single bond. So okay, bang. I got hexane. That's done. So there's your carbon chain, right? What's hanging off the carbon? There's a methyl group hanging off the carbon. All right? So it's methyl hexane. But wait a second here. This is new. Now, the reason why we have to put a 2 here, and I want you guys to write this down. If you have to put a number here into your name, that means that this methyl group can actually go somewhere else. Now, hypothetically speaking here, I'm going to move this with my eyes. And maybe I can somehow... where's that? That's what I'm looking for. Maybe I can replicate this. Okay. So, here we go. Now, I'm going to... This is it right here. So there's my methane group. And why is it a 2? Because you go from the shortest side. Now, where is this methyl group here? Okay, is it closer to this side or is it closer to this side? Remember, we're thinking 3-dimensional, right? So you go to the shortest side, which is right here. 1 carbon, 2 carbon, 3, 4, 5, 6. We got hexane. Good. But where is this methyl group? It's on the 2 carbon. Okay? So that's why this is 2-methylhexane. Now, let's delete this and put this guy over here. So this doesn't exist. This is just, and this guy is over here. It would still be 2-methylhexane. Why? Because, oh, come on. Why is this thing on the, there we go. Think about if you flip this molecule around. This methyl group would be on this side over here. And you always go to your shortest side. 2-methylhexane. What if I move this methyl group to here? So it doesn't exist here. It exists here. Well, you go to your shortest side. Is this my shortest side? 1, 2, 3, 4. 1, 2, 3. So in this case here, it would be 3-methylhexane. What if I move this over here? So it doesn't exist here. It's over here. You can't start counting from this side because it now has become the longest side. And it'll take a little bit of adjustment to be able to automatically see these things in 3 dimension. It takes a bit of time. And but once you get it though, it becomes pretty good. Have a look at this one here. And I put these in here. How would we name... Actually, sorry, I wanted to show you something here before I forget. What if I take this methyl group from here and put it right here? Anybody have an idea of what would happen? And this is an open question.
It will change the whole compound. It's not going to be hexane. It's going to be like the longest going to be, instead of 6 carbon, going to be 7 carbons, I think.
Excellent. Thank you, Elia. That's exactly it. Now, if we move this methyl group over to here, okay, so it doesn't exist here. It's out here somewhere. All right. What's the first thing you do? You count the number of carbons. Find your longest chain. And it could be like, I tend to not, I draw them in a chain for ease of use. But remember, these bonds, single bonds, are rotating. So this thing could look like this. Okay? Doesn't matter. You follow your longest chain. And if this methyl group wasn't here, if it was on the end, okay, well, let's count. 1, 2, 3, 4, 5, 6, 7. This is not a hexane anymore. This is just plain old simple heptane. Okay, so if that methyl group was on the end, now it's a heptane. If it's here on this carbon, it'll be 2-methylhexane. If it's here on this carbon, it is 3-methylhexane. What would it be if it was on this carbon? You would have to start counting from this side. 1, 2, 3. It would also be 3-methylhexane. Try these a couple times here. You've got to be able to think like this, and it will come. It will come. What do we got here now? Whoa, look at this beast. Write the structural formula for 5-ethyl-3-methyloctane. Now, again, if you're naming these or drawing these or choosing the correct one according to ABCD, please always start from the backside. Okay, so 5-ethyl-3-methyloctane. Okay, so I need to find octane. Where's my octane? Well, octane, 8, single bonded. So find me my octane here. I've got 1, 2, 3, 4, 5, 6. Nada. 1, 2, 3, 4, 5, 6, 7. Hey, wait a second. That's heptane. 1, 2, 3, 4, 5, 6, 7, 8. And you see, this is a case where I know it looks like this is your main chain, but it ain't. Sorry, did I just say ain't? Isn't. Jeez. And so you find your chain. 1, 2, 3, 4, 5, 6, 7, 8. So, here's my chain right here. And this is what I do. Like with a piece of paper copy, I'll actually kind of draw a line through my chain so that I know where my side groups are. Because it can get a little confusing. If you're looking at this, it's confusing, and it was drawn to be confusing. Okay? Because I want you to understand that just because you see 7 carbons in a line does not mean that that's your main carbon chain. You're gonna have to find the longest one. In this case here, it dips down. Okay, so there's my chain right there. There's my octane. Now, what do I do now? And you see here, where would I start counting from? Would I start counting from this side? Because I got to label these. Where is that methyl group? Where is that ethyl group? I need to label it. Because this ethyl group could be on this carbon or this carbon. We don't know. So you've got to label it. So after you've got your main chain, go to the shortest side, and that's where you start counting. Okay. So, sorry, I'm just going to try and move these here as best I can, just a little bit. So I start from here. 1, 2, 3. So off the 3 carbon is a methyl group. Okay? And then if I keep going, because you can't start from this side, once you start from one side, you keep going from that side. So 1, 2, 3 is my methyl. And then 3, 4, 5, I have an ethyl group. Now you think, why is the 5 before the 3? Well, the 5 is tied to ethyl, 3 is tied to methyl. We go alphabetic. Okay? So in this case here, it would be 5-ethyl, 3-methyl octane. And it is a puzzle. There is an answer, and as long as you apply the same systematic approach to every single question, it becomes kind of fun. Okay? Any questions on that? I'll take a minute. I'm going to have some coffee. Questions, talk to me. Are we okay? All right. Okay. All right. I wanted to drink more coffee, and I'm going to drink more coffee. Oh, why does that taste so bad? Okay. Let's go. Now we're going to get into a bit of reactions. Simple reactions there, and I will ask you these, okay? And I'll give you real-life examples and these kinds of things. Oxidation, combustion, boom, boom, boom. Okay? You add oxygen there to a system and ignite it, boom, that's what you get, fire. You'll also get carbon dioxide and oxygen. There's a reduction reaction, which I'll show you. I have all these, I'll show you. A substitution reaction, which is just the exchanging of one atom for another. Addition reaction. Excuse me. Two reactants join to form a single product. Elimination. Splitting of those two into two. Let's have a look. Oxidation, combustion reactions here. You'll see here I have methane plus oxygen produces carbon dioxide and water. So basically any hydrocarbon, when it burns in the presence of oxygen, will produce carbon dioxide and water. Any hydrocarbon burns with oxygen will produce these two. Okay. Here we've got methane, and here's the amount of energy that is released. That's what makes your car go or your barbecue tank fire up. Alkanes are a valuable source of energy due to their ability to react with oxygen. Alkanes release a large amount of energy, and they are generally limited in reactivity, other than adding a catalyst there to speed things up. But that's basically all you can do there with these guys here. I'll show you some more though. A reduction reaction. We're reducing. So you have a look here. Here I have carbon dioxide and hydrogen. And what we can do is we're going to break some of these double bonds here. In fact, both of them. So I'm going to break this bond, break this bond. So now I can add more hydrogens on here. And here we've now made an alcohol. And without going into any detail, you guys are all smart. I know you guys are. Probably one of the smartest groups I've ever had for chem. You guys are still here virtually doing this. Man, you guys are outstanding. Have a look at this. Make it make sense. We'll get there, probably week 3. Methanol. Meth. And it's an alkane, right? Single bond. And then all is the name for an alcohol. We'll get there. Substitution. Have a look here. Here I have methane and bromine gas. And what happens is one of the bromines jumps right on there. And here we've got hydrobromoas. Oh man, I don't know what's wrong with me there today. I think a bad egg salad sandwich. I probably had 3 hours sleep there last night. But have a look here at this one here. Hydrobromic acid, thank you. That was bothering me. Have a look at this one. Make it make sense. Here I have bromomethane. And you'll notice that there is no number on here. There's no 1, 2, where. Remember that all of these guys are rotating around. So bromomethane. This bromine could actually be over here. Could be up here. Could be over here. But there's one of these bromines on here. We call this bromomethane. You can have chloromethane. You can have dichloromethane. Dichloro, 2 chlorines. Trichloromethane. Okay? these kinds of things. We'll get there. Addition reaction. Here I've got a double bond. And have a look at this. I haven't really showed it to you yet. How do I name this? How many carbons? Find my longest chain. Well, I got 2 carbons. It's an F. Whoa, I got a double bond. It's an ethene. That's the name of this, ethene. And if I add this acid here, look what happens. We break the double bond. So an addition reaction breaks an alkene. An addition reaction breaks a double or triple bond. Okay, and now look at this one here. Make it make sense to you. What is the name of this? First thing, find your longest chain. Carbon, carbon, 2F. Single bond, ethane. And you remember you work backwards. And I've got this bromine on here. Bromoethane. But wait a second. Can anyone tell me why this is not 1-bromoethane? If I put a number in there, that means that there's another possibility of a number that side group can go somewhere else. What if I put this bromine over on this side and bring this hydrogen? So in essence, what I'm doing is, you can kind of see, you'll see that if this bromine is here, or here, or here, it's still the same thing. And if this bromine was over here, or here, or here, can't you see it would be the same thing? All I did was go like this. So it doesn't matter if this bromine is here, 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 and in this particular case here, we don't need to add a number because there's no other possibility of where this bromine could be. So an incorrect answer would be 1-bromoethane, because here bromoethane is the only possibility. There's no instance there of another. If you're going to say 1-bromoethane, then you need to investigate if 2-bromoethane will exist. And in this case here, there's no such thing as 2-bromoethane, okay? Because there is no 1-bromo. It's only bromoethane. It'll make more sense. It's all right. And I think this is the last one there that I want you guys to know of these reactions here. The elimination reaction. And you'll see there that it's just the opposite of the addition. So addition and elimination are opposites. Here I've got my bromoethane and I convert it back into ethene and my acid. Let's have a look here. Classify the following reaction. So here I have this one here. And what is this? Anybody have a name for this one? Now, I've got 3 carbons and they're all single bonds. So that would be propane. And I've got my hydrogens here, but I got a chlorine on here, which could be on here, which could be on here. Now, what would be the name of this one? Do I need a number on here or don't I? And in this case here, this would be 1-chloropropane, because this chlorine could be here, here, or here in all 3 positions, because these bonds are rotating. This chlorine on this carbon here, it would all be 1-chloropropane. But what if I put this chlorine onto here? I could have that chlorine onto here, and it would rotate here. So in this case here, it would be 2-chloropropane. If I had this chlorine on this side, can you see that it would be 1-chloro again? Hopefully there you guys can see that. And if you can't, let me know. We'll sort it all out. And you'll see here, classify the reaction. Here I've got 1-chloropropane, and we break it up. that is your elimination reaction, exactly the same as this one right here. Okay, so that's a great exam question, test question, assignment question right there. Okay. What else we got? Classify the following reaction. So here I've got chlorine gas and propane. What would be the name of this one? One, two, three, propane, 2-chloropropane. Okay, and you'll see there the substitution reaction where one of these guys just jumps right on here. That's how this one goes. Okay, and you guys have these here. Again, you really don't have to memorize them. You can just write them down and have them there in a testing situation. You know, so which I really don't mind. Like, do you think doctors memorize everything? No. You ever been in a doctor's office and you didn't see a big bookcase with $800 textbooks sitting behind him there or her, and they're all over the place? No, because when a doctor doesn't know what's going on, goes and checks their textbook. And you don't have to memorize all this stuff. You just have to have it readily available. Okay? Cycloalkanes. Again, these are alkanes. Carbon, carbon, single bond. But because they're in a ring structure, this is their chemical formula, which you will notice it looks exactly the same as an alkene, double bonded. All right, these guys here, they're carbon-carbon single bond, but they've lost a couple hydrogens there because they're in a ring structure. How do these guys work? It's all the same banana. Find your longest chain. 1, 2, 3. Okay, so that's prop. They're all single bonded. Propane. This is a cyclopropane. That's all it is. Here, cyclobutane, cyclopentane, and can I move that down a little bit so you guys can see? Cyclohexane. All right, that's how these guys work. These guys are actually more reactive because now you're confining these. Like, there was already a lot, like normal propane, an aliphatic chain, carbon, carbon, carbon. There's already a whack load of energy in there. And you add some oxygen to that and an ignition, boom, boom, boom. Propane, gas, your barbecue tank. But cyclopropane now, you've taken all that energy and now you've stuffed it into this. And those carbons, they are not happy because they don't want to be around that close. So this molecule is already volatile. All right, so these guys here are even more reactive. Okay. Draw the structure for 2 cycloalkanes that have the molecular formula C4H8. Ooh, I like this one. So here now we've got isomers, okay, of C4H8. And there we go. There is your cyclobutane. Ooh, any idea what you would name this one? Start from your base. Okay, 1, 2, 3. Okay, so that's a cyclopropane. And I've got a methyl group on here. So wouldn't that be methyl cyclopropane? Once you see the strategy behind this, it carries the way all the way through to week 13. Even when we're dealing with amino groups, amine groups, carboxylic acid groups, everything follows the same. You find your longest chain of carbons, okay? And that's your chain, work backwards. Let's say it's hexane. And then you draw a line through it, find your groups, your alkyl groups that are hanging off of it, all right? And if you need a number, use it. If you don't need a number, don't use it. Would you need a number here for this methyl cyclopropane? Would you call this 1? What if I had this methyl group over here? Nothing changes because all you're doing is basically rotating the molecule like this, and then you could rotate it. It's all the same, so there is no number needed in this case. Sometimes you do. Naming cycloalkanes. Okay. Please notice these are the same banana. Okay. So this is cyclohexane. And this is methyl cyclohexane. This is the same thing. I've just turned the molecule around. It takes a little while to get used to that, but you have to be prepared to start shifting things. It's more conceptual. That's the difference between the first half of this course and the second half. The first half, X is equal to 2. But here now, you've got a bit of flexibility. Don't get caught. Expand, see the three-dimensional rotation. Okay. Yeah. You'd name the number ring, find your location on it, and let's have instead of me just doing that, have a look at these ones here. Sorry, I guess that looks a little stretched. All right. Now it even looks worse. Good. I know. We'll just move this down a little bit. There we go. So I've given you these structures here. Here are the names. Make it make sense. A, B, C, D, E, F, G, A, B, C, D, E, F, G. Here I've got this one here. So you've got your cyclohexane. Start from your back end first. Write in your cyclohexane. So here I have a methyl group and another methyl group hanging off the same carbon. So in this case here, it would be 1,1-dimethyl. Now, whenever you have two of the same group within a given molecule, you got to have di. If you have 3 alkyl groups in a given molecule hanging off here or there, you got to use tri. Look at this one. Same thing now, but I've moved one of those methyl groups over here. And you'll see here, it's now 1,2-dimethyl cyclohexane. 1,3-dimethyl hexane. 1,4-dimethyl hexane. Doesn't go 1,5. Remember, you always go to your shortest side. So this one here, now we can start counting the other way. This is 1,3-dimethyl. And you see here, can you see it? E and C are the same. We've just rotated them 360 degrees or 180. Oh man, I'm going to have a nap after this. And you'll see here that B and F are the same, and G, what is G here? G, 1 and 2 dimethyl. So have a look at these, and the only way to do these is just to try them out. And then all of a sudden, after 3 or 4 tries, bang, the light bulb comes on. You don't need to do them all, but they actually become kind of fun if once you get it. And you have a look at this one here. Write the structural formula for 1-bromo 2-methyl cyclopentane. Let's just deal with that one first. I know it looks kind of scary, but don't let it. See if I can get all this into one. All right, so 1-bromo 2-methyl cyclopentane. Start backwards. So you get, if I ask you to choose which A, B, C, D, which one is 1-bromo 2-methyl cyclopentane? Well, start with your backside. So cyclopentane. Okay, 1, 2, 3, 4, 5. Okay, so that's my cyclopentane. Now, on the number 1 carbon, I have a bromo. Now, where you choose to start number 1, I don't care. You could start number 1 right here. Doesn't matter. Wherever you want, as long as you systematically do the same thing, you will get the same answer. So you got, on the number 1 carbon, you got a bromine. So here, I'm starting number 1 right here. So I got a bromine. And then 2-methyl. Well, right there, 1, 2. So there's my methyl. If I count it this way, 1, 2, and I put my methyl over here, same banana. Same thing and no matter. Okay? So let's try the next one. 1,1-dichloro 3-ethyl cyclohexane. Oh, this is nothing. Wait until you see. They can get kind of crazy. I tend to cap things at around oct, maybe non. But oh yeah, these things can go on for 50 carbons. It is ridiculous. And you have a look here. Again, start from the backside. Cyclohexane. Okay, 1, 2, 3, 4, 5, 6. All single bonded. All right. And please note that there's a carbon here. And there are 2 hydrogens coming off of here, here, here. There's 1 hydrogen coming off of here and 2 hydrogens coming. I'm just being lazy. The same thing here. Carbon has to have 4 bonds. This carbon is attached to this carbon and attached to this one. Well, that's only 2 bonds. You got 2 hydrogens coming out here that we're just being lazy. So there's your cyclohexane. Now, I got 1,1-dichloro. So, okay, I start here. I could start here. Doesn't matter where you start, as long as you stay consistent. So, 1,1-dichloro. And just because they're on the same carbon, you better write 1,1. You got to tell me, di tells me that there's 2 chloros, but this is the only thing that's telling me where those chlorines are. So, if you put 1-dichloro, it's wrong. Okay, be specific. You tell me where everything is. So 1,1-dichloro, those are hanging off here. And then 3-ethyl. Okay, so 1, 2, 3. And there's my ethyl group hanging off there. That's how you do these. And that's all I got. What do you guys got questions? I think you guys are going to do just fine. I think marks are going to go through the roof on this half. And I really want them to. And the only way to do these is to practice these out. Expand your mind so that you can kind of see 3-dimensionally and go, oh, that's the same thing. That Ian. All right, so that's what we're looking for. Talk to me. If you guys have any questions, stick around. If you don't, get out of here and enjoy your day. I can see the sunshine, which is why my eyes are squinting because I never get to go outside. Just start sleeping upside down like a vampire. But let me know how you guys are doing. You guys are great. Keep on trucking. Keep asking questions. Thanks, guys. And I'll post this there to YouTube in like 10 minutes. Well, it makes me happy. I'm glad you guys are good. Don't fret. You guys are great. Keep on trucking.
Awesome. Thanks, Ian.
No, it's all good. My pleasure, Jennifer. You be safe and be well. Cheers, Elia. How are we doing here? You guys got any questions? No? Enjoy your day. Abigail, you there? No? It's all good, Abigail. You take it easy. If you have any questions, you just let me know. All right? Bye. Now, stop this.